So we've learnt strips, situation calculus. We've learnt strips, event calculus, and situation calculus. And we learned partial order planning and graph. And in the tutorials, I think we applied those to the first one. Can you apply those to event calculus and situation calculus as well? Because I think in a past paper.
What do you mean apply to? So the actual, the planners, the two planners we've done, graph plan and the partial order plan, work with strips representations of
strips,
works with strips. Of course, there is, as I hope I have tried, I have conveyed to you, there is a correspondence between strips. You can take a strip domain and write it in the event calculus, or write it in the situation calculus. So if I am asking to take an event calculus specification of a domain and apply graph plan to it, you first need to map it into strips.
Oh, okay. So whenever we write our graph plan.
Did I ever ask that?
It was like a past paper question, like in 2006, so maybe.
Okay.
But yeah, so when you're drawing your graph plan, you should always write it in strip. Like
yes, because graph plan is defined for strip specifications of. But as I said, strips is the least general of the frameworks we consider, and indeed we've done the event calculus station calculus to show how you can have more general things. But we haven't really exploited the event calculus and situation calculus in their full potential. So we have focused on their fragments to deal with the strips case.
When we're meant to apply abduction to something represented in
abduction is what
yeah.
I've used your example with the Martian system class.
Oh really?
But not with you being sick, with somebody else. Okay. Sorry.
If we're meant to apply abduction to something written in event calculus, we just treat that like what would you expect to see? Would we just treat it as a logic program?
Well, the event calculus is a meta in quotes logic program. The way I've defined it, because I've defined it with holds P, but you can write it as a standard logic program where you don't have the holds. I mean, it's meta because it's holds of a property.
So we don't have to write all the holds.
But you could, yes. What I'm trying to say is that there are alternative ways to write it. So, but the event calculus is a logic program, and if you treat happens as abducible, it is an abductive logic program. You see, it's an abductive logic program because you cannot prove. So that's a clear-cut case of what can or cannot be abducible. Because if I'm trying to plan and I am, I want to get a coffee. Okay, that's my goal. Hold that Francesca has coffee at 11:30. Then I'm going to have a plan. The plan is that happens. I go to the senior common room and buy the coffee and do a number of actions. Okay, so those actions haven't happened yet. So all I can do is abduce them, hypothesize them, so that they form my plan. And then I go off and execute them. So the event calculus and situation calculus model feed into this simple planning agent that we have seen, in which the agent first represents the words, then it plans, and then it executes the plan. So the event calculus with abduction can be used to support that process, the reasoning process, the planning process.
I mean, in like an exam question, if you asked us to find prove an observation using abduction, would we just do it as if like in the example in the slides, as if it was prologue?
Yeah, because it is a standard abductive logic program. So if I'm telling you apply the standard operational semantics of abductive logic program to build a plan for this goal in the event calculus, then you just apply the standard machinery we saw using generalized modus ponens, the way we called it, and when you hit an abducible, you put it aside in this E structure. When you hit the negationist area, literal, you start subsidiary computation where you try to disprove the negation of the negationist area, and if you hit abducibles there, you store them in this separate data structure in node. That's what you do. Any Any doubts about anything? I think it's clear.
I just have a question. Could you go through again the unification part?
Unification
example.
Okay. Everybody has their so Marcus has the abduction and Ursula has the okay, good. Unification is about making two things the same. Okay, put very crudely. There was up there, I haven't written it, but there was a unifier. Okay, so suppose I've got, okay, Italian, Francesca, okay, and, I don't know, Italian, Mario. Do they unify? Can they become the same? No. How can I make Francesca the same as Mario? Francesca is Francesca, Mario is Mario. Cannot be the same. Okay. How can I make them the same? Can I make them the same? Yes, how? I say X becomes Ft. And we can write it like this, but that's what it means. Okay. Now, mother of X. Can I make them the same? Can I? I cannot, because this is a person Ft has a name, and this is mother of. So there is no way. The way I've written it, okay, I'm the mother of somebody, but the way I've written it is Ft. So this is not, it cannot be the same as this. It's like if I tell you, you know, can 1 be equal to plus 2? It cannot be. Okay? So in this case will be that. Okay? So you've got to look at this syntactic. So it's about taking two atoms with the same predicate. Because, you know, I think in one of the past I had at some point written, you know, can whatever P of X unify P of X with Q of 1. Of course they cannot unify because P and Q is Q, they cannot unify. Okay? So they need to have the same atom. And then you just make the two arguments the same. Remembering that constants cannot unify with other constants. So Francesca cannot unify with Mario. Remembering that the constants cannot unify with function symbols. Okay? And then in some cases, you can't really unify them because it goes sideways. So if you get that x is equal to a function of x, then they cannot possibly unify. So always remember, your aim is to make them the same. But you cannot make two constants the same. You cannot make a constant the same as a function symbol. Yeah?
If, say, for example, in this you also had, say, Mario's Italian and Mario's mother is Ft, could that then unify because if X was Mario, then 50%?
But then, what you said is two different predicates. You said Mario is Italian, and Mario's mother is Ft, is mother of Mario Ft. How can they, I mean, it's two different predicates.
No, but if they were also known, then could the other two statements?
So, but then we get this. That's what we would say. We would say.
Okay.
And these cannot be the same. Yeah? No, because.
Mother,
But one thing is to say Ft. One thing is to say that Mario's mother is Ft. They're not the same thing. Okay? So think of it in terms of if you were to write an if then else in Java. Okay? And if then else, you have a guard, you have a condition, you need to check whether it's the case whether it is true or not. So would you say it's true if you say ft equal mother of minus ft? You would say it's false. I mean, I'm putting it very crudely. I hope it's fair. Okay? Anything else that is puzzling? Because these are the only two puzzling things, abduction and amplification. Negation is failure. What's a beautiful thing. Okay, negation is failure. Let's do a small example. You want a realistic example or you want a business use example? Huh? Bien. Okay. Suppose got P is Q and not R. Not there. Up. And then we've got U, T, not S, and we've got S, E, not T. I don't know what's going to come up, but let's just throw some things there. R and Z, E, T, Q. Let's start with these and then we'll see whether it makes sense with them. Okay, we want to prove P. P is our P. What would we do? Come on, everybody, let's have a look at
whenever there is an empty element like Q, then you can follow the...
Well, first you need to introduce Q. So first you say, okay, P, I apply generalized modus ponens. For this rule, this they have in matches. We are going to have also one variables if you want to get them. At the moment, that's without the proposition. So first I need to say, to prove P, I need to prove Q, not R, and not Z. First. Then you say what you say. Q, I need to prove Q. Now, suppose we are using the leftmost selection function. We choose the first one on the left. Is this, there is only that here, and then it becomes this. Q. Okay. Q is not X. I replace Q by not X. Okay? Generalize modus ponens. And I still have not R and not Z. Leftmost selection function tells me now deal with not S. How do I deal with not S? Negation is very literal. I open a subsidiary computation. Okay, let's go here. And what do I want to do in it? I want to disprove S. Okay. Right? So, right. S. S holds if not T. Let's make it a bit more and not A. Oh, actually A. So I also have it. So S holds if not T, but S also holds if A. So I want to say no matter what. So I want to try and prove all possible ways and fail on all of them. Now let's start with A, which is simple. Can I prove A? No. Okay, good. No risk there. Okay? Can I prove now not T? How am I going to prove not T? It's a negation failure. I have to open a subsidiary computation. But, whereas here I want to fail, succeed on T, then I am there here. Can I succeed on T there? Can I prove T? No. Ah, we are going to undo this, but anyway, for the moment. Start, because I succeed here, which means I fail here. Okay? Because here I want to fail in all possible ways, but I cannot fail here because I cannot fail in here. Okay? So, this is like saying I'm going to pass the exam if I don't make mistakes. Okay? And I make mistake. I don't know, does it make sense? Help me to make it. I make mistake if I don't sleep the night before. I don't sleep. So, have I slept the night before? I haven't. I haven't slept. Okay, which means I'm going to make mistakes. Which means I'm not going to pass the exam. Okay? Can you see? To sleep the night before. Yeah.
But you succeed when you try and do the A, right?
Here, it was that, I'm going to make mistakes if I don't sleep the night before, and I'm going to make mistakes if I get drunk. Did I get drunk? No. Okay, fine. At least I didn't get drunk. But did I sleep the night before? No, I didn't. But there are two ways in which I can make mistakes.
Yeah, in the general case, you might need to create variable bindings.
Yes, so let's do one with variables.
No, I just mean
yes,
for the negation as failure case. I remember from Prolog that you don't create any bindings.
So what happens is that the negation as failure is guaranteed to be correct only if the selection function is so-called fair. Fair means that you don't select the negative literals unless it is granted. Okay? So this is down to the selection function. If the selection function is fair, which means it will only pick something when it's no ground, then you're fine. Otherwise, you can give unwanted behavior. Okay, suppose now we have adaptive logic programming. So this is our theory, and our set of potential hypothesis is T. It needs to be a set of potential hypothesis. Okay? It could be T, and it could also be A. Okay? Now, what would happen in this case? Okay, so when we start, because it's adaptive logic programming, we start with an explanation, which is N. Okay, here it's all fine. We get here. Let me undo the. So we start here. We get here not S, S is not T, A. Am I failing on A? Yes, I'm failing, but let me remember that A should never be abused. Because if I abuse A, here I succeed. I don't want it. Okay? So now not T. T. Nice. Abduction, I can abuse it. I'm going to have my E. Now it's going to become T. By doing so, I succeed. Since I succeed there, I fail here. Okay? What does it mean here? Abusing T means I'm deciding now, I'm planning, I am going to sleep the night before. Okay? That's what it means. I am planning to do that action. So I am putting it in my E. So it's like I'm going to pass the exam if I don't get drunk and I sleep the night before and there are other things we have to consider. Okay? So what happens now? Right. We are okay with no tests. With that, with no tests, successful. Now we can't finish though because we still have got no R and no Z. Okay? So it's you pass the exam if you don't make mistakes, you don't copy, and you don't beat up the lecture. Okay. Something like that. Okay, so there are other things that, that you need to consider. Right, nota, let's see what we have up there. We need to open another subsidiary derivation for R. Can I prove R? Can I prove R? No. It's not a potential hypothesis. Fine. Okay, let me then go back and say, Notari is left with R. I'm left with no Z. Okay? No Z. I need to open further subsidiary computation, which is Z, for a plane on Z. Now I've got one way to put Z. One is T. So one way which is T and Q. And now we can start seeing troubles. Okay. T, now T is in my E. I need when I put something in E, it's like temporarily I am adding this to the problem. I'm using it as if it was a snap, a clause with no condition. So I'm going to say, fine, T is there, I still have got Q. What can I say about Q? Okay, Q I have a rule. Now, we are not intelligent human beings here, we are a stupid computer that applies the algorithm as it is defined. So I've got Q, I've got a clause, I'm going to say not S. If we were intelligent human beings, we would see that we can't both fail on Q and succeed on Q, because here we have Q. But we are doing it exactly as a machine would. So from not S here, negation is failure, we need to open subsidiary computation on S. Okay? So let's do that. And we want to succeed. S, there are two ways to prove S. Let's start with one. A. I need to obtuse A in order to succeed here. But there is even no. Cannot. I remember that I didn't want to obtuse A. I didn't want to stay sleepless the night before. No? I didn't want to. Okay, so I'm going to, or whatever that was, I can't remember, it was sleepless or something else. No, getting drunk. I didn't want to get drunk. Okay? So I cannot get drunk. Which means I need to backtrack and try another way to prove S. Not T. Okay, not T negation hysteria. I need to open another subsidiary computation where I want to disprove this. You can see I'm using this different convention. When I want to prove something with a single line, or I want to disprove it with a double line. That's just for visual light with mathematics. Okay? So T. T is in E. Which means, unfortunately, I succeed here. Which means I fail here, too bad. Which means I succeed here. Which means all this work for nothing.
So could you just remind, when do we add to E again?
We add to E when we encounter a hypothesis in while trying to prove something. So this is the single this. We add to E naught when we encounter something when we're trying to disprove something.
It's not related.
Okay, wait then, let's see whether everyone is clear with that, and then we get back.
So, in order to have to add something in, we must not have it on the root, right?
On the?
You can't have it on the root.
On the root?
On
What?
the roots.
On the roots.
Yeah.
Something in A, J.
Yes.
So what we are assuming, and this is your loss of generality, is that you choose your hypothesis amongst things you cannot prove.
So you are a temporary root.
And putting things in E means you are temporary. So for the sake of proving that observation, so I'm trying to prove, I'm trying to explain why Marcus is pain, and I'm making a hypothesis that maybe Marcus is sick. which is not optional. You know, this is, I don't know. Do I know? If I have a rule that says Marcus is sick because the doctor told me, I don't need to make a hypothesis, I know. Can you see? So you choose among the things you can't quite see. Okay? Can we move on to the other style of question then?
I was wondering, can you explain a bit more about the resolution view?
The resolution view. So you can actually view clauses either as disjunctions or as implications. Okay? So you know, if you have that A implies B, this is equivalent to logic to not A or B.
Yeah.
So you can see, now I'm going to do the simple form, the solution saying because A implies B, you have A, then the resolution tells you you have B. But this is the same thing with not A or B, you have A and not A cancel each other out, and you have B. So the standard resolution view is this.
So it's just repeatedly applying the resolution inference rule.
Yeah, but yes. So it's just repeatedly applying that, but you can apply this in this format or in this format, depending. It's a matter of taste, really, because they are completely equivalent.
Okay.
But I like for you to be able to understand, you know, to play with both. So sometimes I do ask, do it in both ways.
Yeah, because there's one possibility question to that. Also, like in the slides, the example of the resolution view that you gave us, it seems that you would start the resolution view after you have found out like what the criminal is, instead of like using the resolution view to find the person.
Well, no, I guess the point is like in this example on the board, you want to prove P, you don't know that P is the case or not, so you are trying. So this method here is basically applying this view of resolution backwards, and this generalized modus scoring, starting from what you are trying to prove. But you don't know that you proved it or not. Here we went through, we filled up the board and then we said.
Yeah.
So in the case of Colorado West, we succeed, but you didn't know. We were trying to prove it.
Fair enough.
Okay? Anything else?
Can you show the resolution in terms of the password question?
Can I show
There
you?
is a password question, it says apply resolution.
As a matter of principle, I don't do past exam questions for the simple reason that
Just for the first two steps. So
no, I don't want to do it because it's one of your colleagues is not here, and then at the end we'll say, oh, you did that, and I wasn't there, and then it's a problem. So I do any examples if you want, but not the past. Sorry, I mean I hope you understand that there is an issue. What was it? That view. You want me to do it for this one here? Shall we do for this one here? However, for this one here, we can't do straight resolution to the negation instead. Was that negation instead and there? Okay, so let's do an example here. I'll make it up. I'll make it simple. So if you have P of X, Q of X, and R of X, and then you've got floor 3 and the R of 2 and R of 3. Happy with this? Very simple. Okay. So what happens is that these are already in standard closure form. At this junction, there is nothing. In this case here, this is equivalent to not R of X, or not Q of X, or P of X. Right? That I'm right? Okay, so you're trying to prove P of X. Let's put it down here.
Excuse me.
Let me switch this off.
Excuse me. Can you use a better marker?
Yeah. you add the negation. Okay? So now, we've got not P of x, you've got P of x or not Q of x or not R of x. You one, so you apply resolution to these two, and you obtain not R of x or not Q of x. Right? Okay, now you claim this is a new clause, you put it back into the pool of clauses. Now you say, okay, not R of x or not Q of x, I've got, let's do the clever choice, I've got Q of 3. Okay? Q of 3. I'm going to get not R of 3, because here I have unified x. Okay? I've got not R of 3 and R of 3. I finish. Now suppose I wanted to do it this time. Okay, I want to do it this time. Let's do this. I'm starting. I always like to put a question mark just to indicate what's, I mean, that's what standard. It's also following the column convention. Oh, P of x. P of x, closed. I am full. Q of x, R of x. Let most. Q of 3, I get R of 3. X is R of 3, R of 3. And you see why we use this symbol to indicate success, because that's the end. Did it happen? Okay.
Sorry, why do we start off with not P of x?
We start not P of x because according to the resolution view, the resolution rule says that from a certain knowledge base, you can entail, I think in the notes I said S, possibly. You can entail, no, I think it was, I don't know what I said, anyway, it doesn't matter. From a certain knowledge base, you can prove a certain S, okay, if and only if KB union not S, or and not S, is inconsistent. So that's what we are doing here. We are adding the negation and we are proving inconsistency. Look at the inconsistency. R of 3, not R of 3. You can see it hits you in the face. So that's what we are doing.
Why is it the square there at the bottom? Because I always think...
Just convention. It's just the empty clause, which corresponds to false, is written like this, but this is we could have written false. Not fussy about these things. I mean, that's what is used in the literature. That's what you find everywhere. But then it's false. Yeah?
Yeah, apart from having... Isn't that at the top one? Isn't it true what we've proven? Like, so, yeah.
Yes.
So, and so you stop when you get to the
here we take this view.
Right, yeah.
So we are trying to prove x.
Yeah.
S is P of x.
Yeah.
Does it hold yes for x equal to 3?
Yeah.
Here we are taking this views. KB and not S is inconsistent. We add not S.
Yeah, because I see the square on the top one and I think true.
Because as I said, we are, because really this corresponds to this kind of process.
Okay.
Then this is a convention.
Okay.
We use the same symbol, but in this case it means true really.
Oh, right, okay, yeah.
So that's why we use the box rather than true or false, because it depends on the context, it means something else. But as I said, this is just a convention. You shouldn't get confused by these things, because conventions are conventions, you know. If I ask you all possible ways, and there are failed ways that we saw before, I would want you to see that, for you to show me that that backtracking takes place, and say at this point I backtrack to this point and then carry on. I would like to see that.
If you have like a nested computation and you have a lot of bindings you have created, if you then backtrack, what bindings will you retract by then?
All the ones you've done in between.
Okay.
So suppose that, let's consider a very simple example of backtracking here. This very simple example. because I'm here. Okay, let's prove consistency. I don't yet know the x, but I know that I want to do something that, when added to the KB, would make it consistent. Okay, then I unify with one, same thing. I get not R of x, not Q of x. Instead of applying resolution to Q of 3, let me apply to R of 2. Okay? So now I'm going to apply to R of 2. Here, apply resolution. I get not Q of 3. What do I do now? I don't get Q of 2. 2 does not unify with 3. Okay? Does not unify with 3. They are two different concepts. So I need to backtrack. In doing that, I had to. So I need to backtrack. Where do I backtrack? I backtrack at the first choice point. Well, at the closest choice point. There is only one choice point here, because in here I have no choice. I have no choice. Here I have a choice. I could have unified with R of 3, or I could have unified with, as I did before, with Q. So let us backtrack. Which unifier do I undo? This. Okay? So I backtrack here, and I say, let me do with R of 3. And not R of x, or not Q of x. Okay, then this gives x becomes 3, and I get not Q of 3. Now I don't have a choice, Q of 3 there, so I just do Q of 3. Okay. So I backtrack first to the closest choice point, and I undo all the unifications I've done on the way, between that point and now. Okay? Anything else?
Like in section about graph plans, there's a concept about mutually exclusive actions and propositions. Can you explain a bit more about that?
It's fully defined.
Yeah, like.
So this is what other students have asked, because we haven't realized that there are several definitions. So mutually exclusive intuitively means for actions they cannot hold together, they cannot happen together. So I cannot be going and getting a coffee while I give a revision lecture to you. I cannot do the two things together. Okay? And for propositions, it means they cannot be two together. So I cannot be kind of quenching my thirst with a coffee while at the same time making you happy. I cannot. Okay, so that intuitively that's what it means. Now, if you look at the definition of, so this is about for actions, this is intuitively what it means. And it could be because two actions are mutually exclusive because they interfere, or because they have preconditions which are mutually exclusive. Okay? Because propositions can be mutually exclusive. Okay. And then the propositions are mutually exclusive if they are effects of actions which are mutually exclusive. Don't forget that in graph plans, you don't focus on one plan. You keep all possible plans open and on the table at the same time. So you have things which are incompatible, okay? You don't know which one you're going to choose, so you've got them all. So the notion, the one thing that is missing is the notion of interference. The notion of interference is defined here. Okay?
So like it's more of a qualitative thing rather than a fixed thing that you can just apply it.
Well, it depends on what you currently have in the graph, because it's with respect to the graph. So you look at the graph and you say, oh, this action, maybe I am trying to, because with graph plan, you don't keep your goal in mind. You do one step of expansion of the graph, and then you check whether your goals are true. And then when you check whether your goals are true, you're also selecting a plan. But you don't want to select a plan which doesn't make sense. Maybe, I am just having action, talking to you, answering to your questions. These are all actions I can do. And also I have, I can go and get a coffee. That's the other action I can do. So, and I am saying, now in this state I could be standing here and speaking to you, or I could go and get a coffee. Of course, I cannot do them together. And maybe I've got two goals. One is to quench my thirst, and one is to answer your questions. you know, I cannot, at this point, just having one layer of the graph, have that, you know, I'm going to answer your questions and go and get a coffee and see your conversation. I cannot, they are mutually incompatible. So I need to plan a little bit more. Maybe I need to keep on answering your questions, and then when the time is over, I'll go and get my coffee. Can you see? So it's about, because you are putting everything together, it's about labeling things which cannot stay together. Yeah?
And also, like, positive effects and negative effects is just positive visuals effects.
Yeah.
Yeah, so in the exam, the question came up on that. In the tutorial, you had it where you didn't expand it at each time point.
Yeah, I think that the graph, underlying graph plan, can grow pretty quickly, pretty dramatic. So I have only put on slides what could fit on slides. I couldn't really put more than that. Similarly, you cannot put, I mean, you have a bit of an advantage because you have the 2 pages, so you can spread it out. But there is a limit to what you can put in a piece of paper. Also, I said it to your colleagues before, I mean, the point of the exam is not to trick you or not to ask you to do tedious things, just to check that you have absorbed the material. So if you show me you can construct the graph exhaustively, fully, for the first 2 time steps, then, you know, then it's repetitive. But I'm not assuming you to be a computer. So it's fine that you do just that, and then you show me what the plan is on the graph, or, you know, because you have intelligence, you can see, and usually the problems we give you in exams and in the tutorials are small. You know, they're not huge problems. So I expect you to be able to show me that you have understood how to construct a graph, doing it as much as you can to do that. But I won't assume that you do every little bit of it, the same way as I haven't done it in the tutorial answers. And I haven't done it because I'm lazy. I haven't done it because it doesn't fit. It's not, and it doesn't really kind of, that's not the point.
So if you do the first 2 time points, then write down maybe initial students.
Yeah, this I think is important because, you know, and usually the first 2 time steps are small. So something that I said, those that come to the office hours, is that when you write your answers, try to be as informative as possible, but don't be logorrheic. Don't throw everything you know about the subject in the head. So be economical in what you say. An example of a bad answer is one where the student obviously doesn't know the answer and just tries, you know, aims, shoots everywhere. I mean, this is the kind of things that one is upsetting because you need to read it through and look for something of remote relevance, and it doesn't buy many marks. So think before you answer. Don't just start vomiting on the page. You know, be economical with what you say and be to the point and be informative. So, you know, I prefer you to explain to me very well how the first 2 layers of the graph plan graph is, and then giving me 10 pages of description of how to construct the full. So I think you need to be informative but economical with what you write. Also, you don't have a lot of time, so 75 minutes for the 2 questions, and you have reading time, so it's important to make as good use of the reading time as possible. Think before you write.
Would you say that there's a particular topic that we covered that students tend to struggle with the most over the years?
No, I don't think so. I think that, you know, all in all, everybody has their own Achilles heel and strength. It's really down to the student. So I think that what's most common is, as I said, that students show really they don't know what they're talking about by just aiming everywhere. That's quite common. And also that people don't quite read the question. So if in a question, as I often do, if I say, give all answers explicitly, say in this case, and somebody just constructed it and stops there, you know, I have asked you, give me the answer explicitly. The answer is, in this case, I would say, here it would be x is 3. So the answer is x equals 3. That's what I'm after. Okay? Because I have defined the answers to be there, and to be the composition of the unifiers. So often students disregard that and they just don't write. And then this is some points off, because I have some points to go to them. So I think that the common mistake is to write waffle and not to really read the question and does not really answer to what is being asked. Because I can understand the spirit, because you've got a limited amount of time, you've done it, you know it works, and maybe it's not a lot of points that are taken off because of that. But still, you just want to move on to the next thing. But sometimes these things are important. Anything else? So we still have over a week, 10 days before the exam, right?
I don't know if it's too detailed in the passage or not, but like in this question, it's not clear who's the max and who's the min. Because usually the root is the max and like the second level is the min.
This is what this was not my question, but I suppose this is what is done.
Yeah.
You start what is done. You start with the max.
Yeah, because like if you stand it kind of conflicts with the labeling on the table on the left.
Yeah, I think it's the reverse. I think it starts with that one.
So you mean player 2 is?
Yeah.
Oh, okay.
Really confusing.
I don't know because that wasn't my question.
Oh,
It's a really bad rewritten question.
it's a pretty weird question.
But yeah, I mean, if you're uncertain about how to interpret the question, you can always ask. I mean, that's quite standard.
Yeah.
You ask. And if it's something which more than 5 people ask, I would say aloud what they need to do is. So just if you think, the badly worded is all relative, and these questions are written. I mean, we had written them before I taught a long time ago. If you ask me what's in the question, I don't know. What's in the exam, I don't remember. So we write them, and then they are vetted. So they are second mark. The external examiners look at them. At every stage of this process, they are being changed. So everybody makes comments. The first marker writes them. The second marker checks them and makes comments. The external examiner checks them and makes comments. And in the case of this exam, because there are 2 classes involved, there's 2 external examiners. And everybody makes comments. So once they get to you, they are as well written as one can. But of course, written text is subject to interpretation, and no matter how much things are checked, there will only be somebody that thinks that the question is not well written. But as I said, we don't take this process lightly at all, and things are very well proved. And of course, we are human, so everybody in the process is human, so that's why you can ask questions.
Sorry, I think you might have said it up there, just to clarify. In the tutorial, you showed 3 different ways of writing situation calculus. There is like poles and pods and stuff. So you wouldn't be expected to know 3, you just need 1 that's sufficient.
I have written the 3 more because I wanted to facilitate you in reading the literature, because different people in the literature use different ways. So if you go and look at the Russell Robbie book, they choose one way. If you go and look at the Poole and Markworth and Gerber's book, they use another way. So, you need to be able to see that really they are just, as we were saying, in the box. There are conventions to use, and you can change. But if you know the spirit of it, it doesn't matter which one you use. And, I might write it in a question in different ways, and you need to be able to recognize it. But unless I tell you something specific, you can write whichever way you like. I mean, really the difference is not semantic, it's syntactic. Yeah, so it is at the level of, instead of holds 100 and T, this is for the situation for the calculus. Yeah, okay? These will be the same, this is the same as 100, and it's 0. I mean, it's the same concept. Okay? And then the axioms when you write separately, the effect axioms, the condition effect axioms, and frame axioms, or when you combine them together. Okay, it's basically like saying I can write P is Q, P is R, okay? Or I can write P is Joris or R. It's the same thing. I mean, similarly to here. This is the same effect. I mean, there are many ways to write the same stuff, and you shouldn't be getting scared about which way. And you know, I on purpose put several ways because I want it to be organized. Anything else? We are approaching the hour. So remember, sleep the night before, don't get drunk. Always get drunk.